So this talk is about a rocket that exploded 30 seconds after launching because of a software bug. And I thought it was very interesting. I rabbit holed into it super hard like a year ago. And I realized there was like a lot of lessons that are still super relevant to today. But before going into the um, story of the rocket, there's just a little bit of context on how I got to the rocket story. So I used to be a penetration tester. I used to work at NCC Group, and as a pen tester, we just found bugs. Use tools, mostly Burp Suite, because most of our work was on web applications. And yeah, our job was to find bugs every like week or two for different clients. And basically, we were turning bugs into PDFs. Like we were really just working at a PDF factory. And for anyone that's been a pen tester, you know that it gets super repetitive because you're just doing the same thing over and over again. And sometimes like you'll give a client a report and you'll come back like a year later and no one cares. Nothing's fixed. Sometimes they fix things, but sometimes not. So I thought like, oh, like how can I like why aren't they fixing things? Why don't they care more? Like what can we like what am I missing? And so there was a lot I was missing. Like for example, there's this entire field of like intrusion detection, right? And it's like one of my all-time favorite tweets ever. So I realized okay, like pen testing is one part of security, but like what else is there? So then like I moved to the blue team side of things, and I started learning about like how do you prove that software is secure, basically, or working to make a product more secure. So in essence, how do you make a product more secure? There's a really good book by Kelly Shortridge where she says security is a subset of resilience, and resilience is an emergent property of the system as a whole. It's not just by assessing like disconnected components that you get a secure product. It's really like how all of these interact together in the final system. So at a very basic level, you have standards, guidelines, right? Like the DoD Orange Book started like decades ago, where it was like, okay, follow these things to have security, and that's like the basic step. But like in practice, a huge part of it is compatibility with engineering culture. So you would think like, oh, like let me just running static analysis or just how do we avoid bugs in our code? And what's really important is any security program or any tool you implement, you want it to be like actually usable by the engineers without adding friction. You want to have like a culture of like psychological safety where engineers are empowered to like report bugs and fix them, and not like blaming them or like saying no all the time, because once you start doing that, this is just might as well not have a security team at all, because they're going to start ignoring you. So at a high level, let's say you join a company and you want to make a product more secure. What do? You have a bunch of tools. Like static analysis is a big one, and we're going to be talking about that a lot today. But it's also about like assessing your third-party libraries, looking at infrastructure as code, removing secrets from the code. Your pipeline is important. Doing threat modeling, doing trainings for secure coding. So all of those together help make a product more secure. But before we get into the story of the rocket, something happened February this year. I had made this photo for a blog post. I'm not going to explain every single thing, but basically what happened is the White House released this paper. They basically said that the current ecosystem does not sufficiently incentivize the investments required to secure the foundations of cyberspace, which is interesting that the government is caring about this more. I was mostly surprised that they're using cyberspace, like terminology coined by William Gibson in sci-fi books, by like official government communications. But what the paper outlines is three main areas. The first one is hardware. And so hardware is important and interesting, but I I'm not going to cover it today because I mostly work on consumer products. And so consumer products, think like a video game or a password manager or like the Discord app itself. All of those, you want them to run on a wide variety of hardware. You don't want to limit the hardware that your products can run on. So for us, um, we're gonna skip it because the hardware is gonna be whatever the customer wants to run it on, right? To a certain extent. The second point is formal methods. So that's a spicy one. And I'm curious, like leave a comment in chat if you use formal methods in your products. It's easy to recommend to say like, oh, you have to like prove your code is secure, but in practice, it's really difficult to do. So formal methods is just proving your program behaves as intended by creating a mathematical model, like basically using math to prove that everything is correct and it runs exactly as you intended to run. So some microkernels and stuff have been formally verified. It does happen, but it takes a significant amount of effort to formally verify something. When I was looking around to see if something like is there anything in production right now that's formally verified, the main thing that I found is at Amazon, which Amazon has a huge security team, so they can afford to spend time and effort on formally verifying something. So they have S2N is their internal TLS library that they use like for like inter-service communication and stuff like that. So they have this really interesting paper on how they formally verified it. By they did many things. Like it took a team of like a bunch of people like almost a year to have this up and running, and they made some simplifications. They made some assumptions. They wrote a tool that runs in CI/CD, and every time you push a change, it can verify your changes. Um, it is possible. It's great in practice, but it's super difficult and extremely time consuming, basically expensive to actually do formal verification. Um, Another example is I used to work at Activision, so a lot of time I was on the Call of Duty code base. And so imagine like I go and tell them like, hey, can you verify let's formally verify Call of Duty. Like that's not like that's gonna take forever. Like, it's not a practical recommendation to make. And it's also part of the system as a whole, right? Like one of my favorite papers ever is Ken Thompson's reflections on trusting trust, and he's like, oh, what if the compiler itself is backdoored? So like not everything is provable to be right. And we're gonna talk more about the limits of formal verification at the end of the presentation today. And then three, one of the biggest points was memory safe programming languages. So that's a spicy topic, and basically Joe Biden made C++ illegal, right? They were like, no more C++, no more C, no more C++. It's legal now. Just write Rust, right? That was basically the recommendation, which is a spicy take. Many people agree with it. Many people like it. Essentially, around like 70-ish% of vulnerabilities exploited in the wild, like things that have CVEs, are attributed to memory corruption vulnerabilities. So we know that there is a problem, but they're saying like just remove all C++ and then just write Rust instead. Now, it is in practice, it's absolutely possible, right? Like this already happens at Google, for example. There is interoperability between Rust and C++ in Android. But also Google, just 2 weeks ago, they released this interesting paper called Advancing Memory Safety. So essentially, they're doing this, what we just talked about. They want to long-term replace memory unsafe languages with memory safe languages. But they also want to harden memory unsafe languages because they recognize that it takes a lot of time and effort to just replace everything, right? Like again, like I used to work at Activision. Let's say I told them like, oh, rewrite all of Call of Duty in Rust. Like it's like trillions of lines of code. I mean, exaggerating, but like a huge code base. Can you just rewrite everything in Rust? Also like not super realistic, like for some code bases. It takes a huge amount of effort, a huge investment. So for a company like Google, also they have a lot of resources, they can afford to give it a shot. But I'm also super interested in when they mention hardening memories in unsafe languages. How do you do that? So we'll talk about that at the end. DARPA also has this initiative called Tractor, translating all C to Rust. Same idea. Um, Feed it C and it spits out Rust. This isn't even the Rust logo. I don't know what they have in here. Anyway, so back to the actual story of the rocket. So that was all just context. Um, so 1996 is when this incident happened. So 1996 is when Frances McDormand gave her killer performances in the movie Fargo. It's also when Tupac was still alive, only for a few more months, but he doesn't know that. So we're in Kourou, French Guyana. So French Guyana is near the equator. It's a French colony in South America. And Kourou is a small fishing village that's known for launching rockets. So it's a French colony because the European Space Agency is it's mostly French, but it's a European based organization, and that's the organization that's launching the rocket today. The reason we launch rockets at the equator is your exit velocity is faster on the equator. Whereas, for example, if you launch a rocket at the North Pole, you're just like spinning real fast in place, but so like your velocity is actually zero. But if you launch at the equator, the second you're out, like you gain speed basically. You're it's like free speed. So that's why they chose French Guiana, not like France. So this is the rocket launching today. It's called the Ariane 5. Like instantly you notice that it is way chunkier than the other rockets, the predecessors. So you had like a like four. This is the fifth iteration, right? Like the Ariane 4 was wildly successful. It was great. It ran great. It never failed. Um, it worked perfectly fine. But this new version, yeah, they added some power, which is going to be relevant. So keep that in mind. So we know already that the cause of the explosion was self-destruct. Okay, we basically fished out the black box from Guyanese swamp, and we saw okay, it's self-destructed. Great. So now our goal is to figure out why did it self-destruct. So there's this module on the rocket called the inertial reference system. So the purpose of this module is to calibrate the trajectory of the rocket before it launches, right? So while it's standing on its launch pad, the Earth has like gravitational forces and just things that it has sensors to calibrate and see like, okay, as I'm launching, am I supposed to change anything in my trajectory to compensate for like gravitational waves or something to make sure I go to my destination? So this module was on the Ariane 4, the previous version, and they moved it as it is to the Ariane 5 because it never failed. So this is one of their documentation where they show you how it takes it has like gyro and accelerometer, and it uses it to calibrate its trajectory, and it feeds things to the onboard flight system. For example, like do I need to increase my speed during launch, right? So while we're looking at the logs in the black box, so again, logging is very important. Um, we see that the horizontal velocity of the rocket is supposed to be a 64-bit float, but the buffer in the inertial reference system is only a 60-bit signed 16-bit signed integer. So integer overflow. So very quickly, let's just cover some of the basics of what is a integer overflow or a buffer overflow first. So you have a small buffer, you're copying memory into somewhere that's even smaller, or like have a big buffer and you're copying memory into something that's smaller. It doesn't have enough space to store everything you're copying, so it starts overwriting other places and other buffers basically. That's buffer overflow. Now, also in 1996, there was the Frack article smashing the stack for fun and profit, which was like starting to popularize the idea of buffer overflows even more. I mean, they were already starting to be popular, but like this, also released in 1996, which is pretty cool. So in this case, it wasn't just a buffer overflow. It was a specific flavor of buffer overflow called an integer overflow. And my favorite depiction of it is when the miles on your car meter thing like goes to the max, you add +1, it wraps around to 0, right? That's an integer overflow. The buffer can't possibly hold any more numbers, so just like wraps around. So what happens in a language like C++, when you have buffer or integer overflow, is you have undefined behavior. So what happens when you have undefined behavior? What happens is undefined. We don't know. It depends. I don't know what happens, right? Like many things can happen. Some things it's fine. Sometimes it's fine. Sometimes your program crashes. Sometimes it's an exploitable vulnerability. So the idea is like it's behavior that's not been defined, and I don't know how it's intended to behave at that time. So some compilers do have a sanitizer flag to look for undefined behavior. So you can actually try to find those at compile time. Very important thing to mention, since we're, memory safe languages and the language wars are very active these days. The rocket, the Ariane 5 rocket, was actually written in Ada, the Ada programming language, not in C++. And the main difference is Ada has good exception handling, whereas C++ would have undefined behavior in the case of overflows. And specifically here, you see that in the case of a signed integer, in C++ you would have undefined behavior, whereas in Ada it would raise a constraint error, right? So we know that a buffer overflow happened or an integer overflow happened, but Ada can catch the exception, can raise an exception and catch it. We know how to catch exceptions, right? So that's fine. We should be able to handle it right. So far, that's not a reason to explode the rocket. So the Ariane 4 previous version was very slow during launch, whereas the new version, the Ariane 5, super fast. It's so much faster when it's launching vertically. So because of that, the initial reference system, while it was launching, as it's going up, the integer overflow triggers, and that's fine. We're using Ada. We can catch the exception. So the initial reference system sees an operand error. It detects it, and the design decision they had taken while making the rocket was that when you detect an operand error or any error, we assume that it's a hardware fault, like the hardware is faulty, and we shut down the system and kick off the redundant unit, like the backup unit, right? So we caught the error, time for redundancy, so we shut this down. So luckily there's a backup inertial reference system, right? That's how they designed it. So the backup unit, what happens when you give the same system the exact same input is going to give you the exact same output. So it also sees the operand error, it triggers it because the same integer overflow happens, and it also thinks like, okay, time for redundancy and shut me down. So now both of the inertial reference systems are shut down. That's fine. That's fine. Still no reason to explode, right? All we have to do is raise this exception upwards again. So the flight control system, we're going to raise the exception, say like, hey, we both experience an operand error, right? And here is basically the core issue, was that the flight control system wasn't designed to correctly handle errors, exceptions. So it basically interpreted the exception as its ASCII value of like, instead of operand error, it like translated to the ASCII value, which makes a really, really, really long number, right? And so it thought the flight control system is supposed to, like get fed like velocity data. And so it thought like, oh, like I'm actually going really fast. So to compensate for this insane speed, all I have to do is tilt the rocket by 90 degrees, right? So what happens when you have a rocket and it just like does that? You know, like you're going at this like really fast and you just like tilt it. And so here, because the hull is being ripped out by gravitational forces and it's starting to fall apart already because like you're not supposed to do that. The self-destruct program actually works perfectly fine. It works so well and it explodes the rocket. Um, it works well because that's its purpose. It's not supposed to let the rocket start getting blown apart and go into someone's backyard, right? So the self-destruct program worked perfectly well. So that's the chain of events that led to the explosion. But these are rocket scientists. They know what they're doing. It's not random people. It's not like a 3-person startup, right? It's like a heavily funded organization with many smart people. So who wins in this fight? Like the EU's smartest rocket scientists or one operand error? My point is, how did this chain of events even happen? Like, like, didn't they use static analysis? And here's the thing, they actually did, right? So they, while designing the rocket or the software of the rocket, they ran a lot of tools. They followed like some rigorous methodology, and they found 7 potential buffer or integer overflows in the inertial reference system. So they caught they knew about the bugs, right? And remember at pen testing, I was thinking like, oh, why don't people just fix the bugs, right? So let's see why didn't they fix all the bugs here. So they actually had some goals. So one of their goals during the design phase was that the target max CPU utilization should always be maximum 80%. They also read the documentation, they read the comments, they knew that they were writing Ada and not C, and so we can catch the exception. They had like they checked all of the assumptions they had made, and so they realized that the integer for the velocity is never supposed to overflow, right? Like it's fine. We should be able to handle that. So they fixed the ones that they thought might have a chance of overflowing. And the ones that won't overflow, they just left them. Now you might think like, why don't they just fix all of them, right? It's just an if statement. You're just adding a bounce check. So remember when we talk about target max CPU utilization, remember that this is in 1996. Your iPhone, like even a few generations ago, iPhone CPUs is 100 times faster than the CPU that was on the rocket itself. Um, Resource constraints was a real thing back then. So every single computation matters. That's why they were really trying to optimize everything. So part of it was also testing in the production, in that was the first ever launch of the Ariane 5 that exploded. In itself, that was like the first launch was kind of a test. They were like, let's see what happens, and there was like the satellite. There was no people on board. There was this rocket is supposed to launch satellites, so there was like a student project on it. It was still like an expensive failure, but no one was killed. Um, so looking at the design a bit, the assumptions they made was that when they encounter an exception, they log the exception, they store it in memory, and you shut the hardware down. Right? Because at the time they assumed that it's all faulty hardware if they ever encounter any bugs. They also had another design assumption that unless proven necessary, anything that worked fine on the previous version of the rocket, just keep it as it is. No need to actually change it, right? The saddest part is that the initial reference system itself calibrates trajectory before the rocket launches. So why was it even launching after the launch? And so there was a thing on the previous version of the rocket where, like, just in case there was like a cloud that passes, or like for whatever reason they wanted to delay the launch by like a few minutes, it took like hours to reboot the whole system. So they kept it on for 40 seconds after the launch time, just in case there's like a last minute thing, so that they can reboot without having like to wait like hours to reboot everything after it shut down. But on the new model, the Ariane 5, you can actually reboot instantly, so you didn't actually need to have this running at all after launch. Like they could have shut it down like right before launch, and it would have been fine. Even if they had an issue, they could have rebooted fine. So there was really no reason for this to be running at all, and it caused the explosion. After the explosion, so they had like a really good post-mortem. Like they analyzed all of the failures really thoroughly, and they have like a really interesting document that they released. But one of the things they did was they just simulated the rocket launch with all the input and all of the, like they did like a full sim, and that this bug was caught. It actually caught that, oh, there's going to be an integer overflow and this is going to happen, it's going to fail here, right? And the idea is like before the first launch, they hadn't done a comprehensive simulation, basically. So what triggered the failure as a whole? It's all of these together. It's wrong design decisions and undocumented assumptions and software use and unnecessary legacy code and a lack of testing and mishandled exceptions caused by an integer overflow. All of these together caused the exception or the explosion. Notice memory issue not really relevant here because they were already using a memory safe language. So in their post-mortem doc that I mentioned, that's really good. They mentioned that the basically attribute the explosion to a specification and design error, and that there was not adequate analysis and testing. They admit that it wasn't a random hardware failure, but a design error, and they admit that they had the explosion was detected but not handled properly because the exception, sorry, because the view had been taken that software should be considered correct until it is shown to be at fault. And now one of my favorite slides ever is the board, the review board after the explosion. The board is in favor of the opposite view that software should be assumed to be faulty until applying the currently accepted best practice methods can demonstrate that it is correct. I think this is awesome. This is a really cool idea. Now, one of the spicy takes here is like, okay, how do you actually demonstrate that your software is correct, right? That's easy to say, but like, how do you do it in practice? So overall, the Ariane 5, even though the first launch exploded, it still was one of the most successful rocket launches ever. It even launched the James Webb Space Telescope last year. And yeah, its last ever launch was in 2023, and its successor, actually, the Ariane 6, was launched for the first time this July, a few months ago. It's the rocket in the background, not the airplane. And yeah, this is the photos of the Ariane 6 launching, and the first launch was also successful. No explosions, so they learned, I guess. So a little bit in the spirit here, let me know if you get the reference, but exploring the idea of like how do we actually prove that software is correct? Um, I want to cover this other example of integer overflow, or alleged integer overflow. So in the video game Civilization, if you've played it, you know that if you ever play against Gandhi, the second you discover nuclear weapons, Gandhi nukes everyone. So the rumor was that Gandhi was the least aggressive leader in Civilization, and so like let's say like aggressiveness level is 0, and that's and there was apparently like a thing where once you discover nuclear technology, you get -1 to your aggressiveness level, so it underflows and wraps around to the highest level, so it nukes everyone. But actually, the Sid Meier team, like the Civilization team, admitted that this was a myth. It wasn't actually the reason why. I think it was some other bug why he was like nuclear all the time. But yeah, not actually an integer overflow or underflow, even though I still think that's a great example. Um, Another example of just bad software design is the Therac 25. That was like probably like the most brutal example of bad software. It was a radiation machine, but because of bad user experience and user interface, basically the operator was normalized to just click next, 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 and put in changes and next, next, next while calibrating it. But it would like not show errors properly, and sometimes like if you calibrate it while it's already shifting things, it doesn't actually, like the UI would update the new thing, the new like radiation levels, but it wouldn't actually make the change in the machine itself. So because of basically essentially because of bad UI, this killed people. Actually, it actually really gave lethal doses of radiation to people. So these examples were basically of software can go wrong, and how do we prove that it's correct? And so when I was thinking about this, I always think back to this. So in 1931, this man, Kurt Gödel, came up with his incompleteness theorems. And so that's super interesting to me and relevant to like being able to, or attempting to, prove software correct. And so the incompleteness theorems are so basically he found a paradox, and the an example of a logical paradox is like if Pinocchio says my nose will now grow. Like if Pinocchio talks about something external, like this is a truth, or this is a lie, and when you're like, but when you're self-referencing, that idea of self-reference, like my nose will now grow, like if it's a paradox. If he's lying, then it would grow, but then he wouldn't be lying, so it's not supposed to grow, right? I think it might like grow and shrink repeatedly very quickly, but like anyway, like it's kind of undecidable. Like I don't know. So there's a book by Hofstadter called Gödel Bach. It's an old book. It's huge, but it talks a lot about these like self-referential paradoxes and Gödel's incompleteness theorems. But essentially, his incompleteness theorem said that in some systems, some statements are undecidable, where meaning in the system itself, I cannot prove nor disprove the correctness of that statement. And Alan Turing extended that to his halting problem. It's the same self-reference thing, where like if you have a program and given as input, you give it like an algorithm, and the input of that algorithm, it'll tell you if it halts or not, if that algorithm with its input halts or not. But then if you write the opposite of that program and feed it to itself, and it's like it creates the same sort of paradox. And so Turing proved through that um the halting problem, right? Like basically I cannot prove if a program halts or not for any given input. And my theory is that like if I can't prove that the program halts, then how can I prove that the program is secure? Right? Let's say a program that doesn't halt causes the denial of service. Then I can't prove if a program is secure the same way, right? So both of these, like Kurt Gödel's incompleteness theorems and the halting problem, both make us think like, okay, like we say that we want to use formal verification. That's like tying it back to the White House technical report. So how, like, can I actually use formal verification? But like also like is it even possible to prove something correct or incorrect? And these suggest that not really. There's many cases where it's impossible to be able to formally verify or formally prove your program to be completely secure. So if formal verification or formal methods aren't comprehensive and don't always work and not really feasible and too expensive, then what about our third one here, memory safe programming languages? So I might say some spicy takes here, and I know a lot of people disagree, including Google, right? Like Google's going through the effort to write more Rust. But yeah, I'm happy to have a discussion over those in Discord or Slack. But let's talk about this a bit more. Memory safe programming languages. And so essentially these days we have Rust and C++ that are competing. Um, Now, obviously, memory safe languages, you have many. Like Ada itself, the one used on the rocket, was memory safe. And the explosion still happened, right? So it's not everything. But Python, for example, is memory safe. Java is memory safe. Go is memory safe, right? Um, Rust is appealing nowadays because it's supposed to be fast. So it has use cases where it can replace C++ without a major performance hit. And C++, or at least when I say C++, what am I talking about? Like, 'cause C++ itself also changes, right? Like we have C++ 23 is the most recent version. Um, so C++ itself right now is not out of the box memory safe. And so um, I got an interesting comment by Lust Grunt saying that they will personally be arresting all C++ developers after the con. That is correct because it is officially illegal to write C++. Um, so if you had to choose, which one would you pick? And I think like it's fair to say like if you're starting a brand new project right now, like you can pick whatever you want. Like it doesn't matter. It's a new project. You don't have tech debt, right? You can pick any language. Um, the real challenge is like when you go into a company like Activision, they had Call of Duty, like many lines of code already written in C++. Um, so yeah, uh, keep in mind that like Ada itself was used on the rocket, and we know that Ada is memory safe, but the rocket still exploded. So as we're talking about memory safety, even though they say like okay 70% of CVEs are memory corruption bugs, you can still have devastating bugs completely unrelated to memory safety, like logic bugs, threat modeling errors, oversights, right? All the things that we saw in the rocket, these are all relevant and they continue to be relevant regardless of memory safety completely, right? So memory safety is not everything. So very important is that there are critical software written in memory safety that are known to be reliable, like um fighter jets. Like here, the F-35. It's mostly C++, right? Like more than half of the code base is C++, and then another third is C. Um, no JavaScript, right? There is some Ada, also no Rust, right? No JavaScript, no Rust. So can you create reliable systems in C++? Yes, yeah, of course. It's you can, right? Like it's not impossible to secure C++, right? And that's one thing I think is not emphasized enough these days when like a lot of people just assume that like it's impossible to make C++ safe. Like I know it's difficult because it's very easy to make mistakes in C++, but it's not over yet. So let's talk about that a bit. So remember, my job was to find the bugs and turn them into reports. So how do we do that? And let's say we wanted to make C++ more secure. How would you do that? So I'm going to spend a few minutes talking about static analysis, and then we'll talk about in more detail about how to make C++ more secure. But first, static analysis. It's a big field by itself. And tying it back to the Kelly Shortridge book, like it's just one aspect of security. And so analyzing one component with static analysis isn't enough to make a whole system secure, right? And it's just one part of the entire tool set. So how do you how do you run static analysis in production? You integrate it into your software development lifecycle. Ideally, run it in CI/CD or earlier in developer's IDE. But at some point, it's running and it's just looking line by line, trying to look at patterns, known patterns of vulnerabilities, and it flags them. A good example is like cipher mode suites. Like this is just easy pattern matching. So static analysis tools can catch like, oh, don't use ECB, use GCM instead. That's safer, right? But it doesn't have enough context. So for example, it doesn't have enough context to say like, oh, you shouldn't be using encryption. Instead, you should be hashing, right? So it has context to do pattern matching, but not enough context to actually go and make like a more strategic recommendation. That's why it's limited. But yeah, ideally you just like tie it into CI/CD. You do a variant analysis, see like, okay, what other versions of this vulnerability I have. Now one of the oh, so some languages like Ruby on Rails, they have like excellent built-in static analysis through like Brakeman, right? So like, and you have RSpec and Rubocop. So like some languages, like you have like amazing static analysis tools, but in others, like in C++, actually, like what would you use? Like that's a bit harder. So there's like CodeQL and some of the more commercial tools. They can wrap around the compiler to generate an abstract syntax tree to more accurately scan C++. But like more recently, SemGrep actually released some change. Actually, like earlier this year, they started improving their C++ capabilities. SemGrep is like one of my favorite static analysis tools. So things are improving in the area of static analysis to try to identify bugs in C++. One thing to keep in mind, I think like the biggest mistake security teams make when triaging a large amount of findings is it's one thing to it's one thing to like run a tool and generate like thousands of findings, but then like it's important to triage them, because if you just ship those to developers without heavy triaging, who's gonna go fix 80,000 findings, right? Like you have to actually triage them, give them actionable remediations, group them together into like fixes, right? Like there's a lot of work to do. You can't just like give developers raw scanner output like, hey, here's 80,000 findings, good luck. They're just gonna ignore you. They're not gonna fix them. Okay, so the last few minutes of the presentation is, can we actually make C++ more secure? Or do we just have to write everything in Rust? So there's a really interesting talk by Bjorn Strautstrup at CPBCon 23, where he mentioned 2 points that resonated with me a lot. The first one was that we should be writing contemporary C++, not C/C++. He's like, what is C/C++? Like who? Like what? That's not a like. You should be using a modern language, right? And you know, we have C++23, and one of the problems is people will pick up a book from the 90s to learn C++, and it's like that's not the same language anymore. Like, do you want to be writing C++98 or C++23, right? And because in the new versions, you actually gain a lot of features you can use that help you write better code. So problem number one is a lot of people use old versions of C++. Now, partially that's due to tech debt. That's fine. It does take a lot of effort to update our code bases. But the thing is, like, if you're gonna spend the effort rewriting your entire code base in Rust, well, surely you can just spend effort rewriting your C++ into a modernized version and reviewing it, right? Another important point he makes that I really like is when he compares C++ to Rust. I mean, obviously he's biased to C++, but he says Rust right now, we see a lot of passion projects by developers, and so when you're looking at the side project that's someone's passion project, like they're really enthusiastic about spending time and effort making the code secure, right? So they're gonna go out of their way to make sure everything's is like secure, everything's like written well documented, everything, right? And so out of the box, you have like a lot of really good Rust projects that have like you know, good quality code that's well documented. But you're comparing that to C++, which you've had people writing enterprise C++ code for decades. Talk to people in a huge company that has thousands of devs where they all hate their jobs. They don't care what they're doing. They're just doing it as a job, right? Like you're not gonna get great quality code there, you know? So it's kind of like an unfair comparison to begin with, to compare Rust with C++. By the time Rust reaches like enterprise quality, the quality is gonna go down, and you're gonna have a number of vulnerabilities there anyway. So Herb Sutter also, he's on the I think he's on the ISO chair to make C++ memory safe, but he has a lot of interesting projects. So he has C++ front, but also he has this really good blog post also from earlier this year where he goes on a large rant on like, okay, but like, can we make C++ secure? And he lists a bunch of alternative or like approaches to make it secure. I think in general, one of the challenges is a lot of people are terrified of backwards compatibility. I have a slide on that later, so we'll cover that in a sec. Another awesome person is Sean Baxter. I follow him on Twitter, and he is super funny. Like he'll tweet things like, "Why is no one else pursuing memory safety in C++?" And then he's like, that's just depressing, you know. But he actually does a lot of work. He wrote Circle, which is like a compiler for a subset of C++ that tries to support features from Rust. Really awesome work. And there's also some um um new features being proposed into the C++ standard, and one example is erroneous behavior. So, for example, we can cause undefined behavior in C++ by not initializing our variables. And so initially I thought like, oh, why don't we just auto initialize our variables, right? And you can technically do it. You can just have a default initialization or let the compiler auto initialize your variables. But I heard a really good argument against it, saying that what are you going to auto initialize your variables to? Like, if you just make everything 0, that's not necessarily correct either, right? Like maybe having my all of my variables be 0 is not correct, and that's also going to cause bugs, and that's going to be even harder to debug because it's not in the code. It just auto initialized by my compiler. So default initialization can cause issues. And so what's proposed, there's this paper where they're proposing erroneous behavior instead. So instead of having undefined behavior, when you have an uninitialized variable, it triggers erroneous behavior so that you know, like, oh, actually there is an error here, and I'm supposed to handle uninitialized variables in some way. So remember at the beginning of the talk we mentioned Google has a paper for advancing memory safety. So some of the approaches they list, so they want to rewrite things in Rust, but at the same time to harden current C++ code. They list like, one is they want to start bounce checking in the C++ library. They have their own miracle pointer that they use in Chrome. They have isolation techniques like sandboxing, so that if you do exploit some sort of memory corruption vulnerability, then you're still in a sandbox, which limits the impact of an exploit. And now they're improving their fuzzing as well, which, like, fuzzing is another popular way of surfacing bugs. And one thing I find interesting is, so C++, a lot of like the C++ standards committee, I think, is like terrified to roll changes to really significantly improve memory safety. One of the reasons they're terrified is that backwards compatibility, right? So they don't want to make a change that's so big that it breaks all of C++ and nothing compiles anymore, right? And so the problem is you have a lot of really old code bases with legacy C++. But what I think is they could just pull a Python 3, right? Like, I know it was annoying porting everything from Python 2 to Python 3, but you can still run Python 2 whenever you need it. And then for new things, you can use Python 3. And so they could potentially do something like that in C++, where if you want the legacy stuff to run, you use C++ old, and then they can fork it and have like a memory save version of C++. It's not backwards compatible, but maybe for some projects that's fully fine. So I have two more slides here before I end. One is, my takeaway is, can you make whatever language secure? Yeah, I mean, we've seen it. You can make any language secure if you put in enough effort. If you really want to rewrite things in Rust, that's fine. You can also spend effort trying to improve things in C++. The industry itself is improving as static analysis tools improve, but also the standard itself gets improvements. So overall, things can explode, but it's fine. Like, the first rocket exploded. It became the most successful rocket ever, and overall things are improving. We are catching bugs. Some people want to rewrite in Rust. Some people just want to improve C++. Overall, things are getting better. And that is all I have for you today. So I'll be hanging out in Discord if you want anything. Drop a comment. I'm nullsec. Otherwise, have a great day and enjoy the next talk.